So to start off, the definition of stoichiometry is the portion of chemistry dealing with numerical relationships and chemical reactions, the calculation of quantities of substances involved in chemical equations. So in Greek, this basically just means measuring elements. And then we have a short reminder that Avogadro's number is 6.02 times 10 to the 23rd, and this is the number of representative particles in a mole. So we're going to start off with this basic unbalanced chemical equation. So as you can see, on the reactant side we have hydrogen plus oxygen and producing water. So we have two hydrogen molecules, and two hydrogens over here, but we have two oxygens and only one over here. So we have to add in some coefficients in order to balance the chemical equation. So we're going to end up coming over here, putting a 2 with the hydrogens, leaving a 1 for the oxygen, and then 2 waters. So now you can see that we're going to have 4 hydrogens over here, 4 hydrogens in the products, 2 oxygens in the reactants, and 2 oxygens in the products. This is further explained here in this little diagram showing the molecules. As you can see, sort of like the recipe to produce water, you've got the 2 H2s, the 1 oxygen molecule yielding 2 water molecules. So as you can see, here's the little, exactly up here, you have 2 here, and you can see 1, 2, 1 here, the 1, and then the 2, 1, 2. So these ratios are like derived exactly from what you need in the chemical equation. And as you can see, here is the molar ratio. You've got 2 moles of hydrogen, 1 mole of oxygen, yielding 2 moles of water. So here we have some things to remember about the coefficients in balanced chemical equations. So for one, that they show the ratio of the reactant and product molecules needed, which was shown in that little diagram before. Also, no matter what the quantity of reactants or products you're dealing with, the ratio of moles will always stay the same. And finally, that the coefficients show the molar ratios. And so this is going to come into hand a lot when we start doing the calculations. So we're going to start with some simple calculations here. So a mole to mole calculation. So if you have 8 moles of hydrogen, how many moles of water can be made? So now that we've identified our givens and what we need to find, we can take our coefficients, the 2 to 1 to 2 ratio, and use that as a multiplier in order to determine how many moles of water we can make from the 8 moles of hydrogen. So we come here, you start with what you're given. So we have 8 moles of hydrogen, and that's just over 1. Next, we need to look at our coefficients to determine what we need to multiply by in order to find what we need. And so in this case, we're looking for moles of water. 8 moles of hydrogen here, and we're going to multiply it by a ratio that we can find from the coefficients in order to get what we need over here, which is going to ultimately be moles of water. So if we look here, the ratio of moles of hydrogen to moles of water is going to be a 2 to 2 ratio. So you're starting with what you're given on top, and that's going to end up on the bottom over here in the ratio. So we have our 2 moles here, so 2 moles H2, and you're getting this from the chemical equation. 2 moles of hydrogen, and then on top, what you want, 2 moles of water. So here, you just multiply it out. 8 times 2 is 16, and you're going to divide that, and then you've got 1 times 2 is 2. So ultimately, you're going to end up with 8 moles of water. Okay, so next up we're going to go over how to do a standard mole to mass question. So first, you're going to want to... So we're going to start with what we have. So we write this out. We've got 3 moles CH4, and then again it's just over 1. So next, what we can get from our balanced chemical equation is the coefficients, which is going to help us put together a ratio to get us to mass of carbon dioxide. So first, we have the moles of CH4, and we know that we can get from here a ratio of moles of CH4 to moles of CO2. So next we're going to get our moles of CO2, and from there we can look at the periodic table once we know the molar amount of CO2 to determine how many grams there are left. So from moles of CO2, we're going to be going to grams of CO2, and this is ultimately where we want to be. So we have our 3 moles of CH4, then we're going to come and get our ratio. And remember, since we started with CH4, that's going to go on the bottom. So from the chemical equation, we can see that there's 1 mole of CH4 used as reactant in order to produce 1 mole of CO2. Okay, so from here we can see that these units are going to cancel out like that. So now that we have moles of CO2, look back down here, we're going to get to grams. So according to the periodic table, we know that in 1 mole of CO2, 44 grams of CO2. And we simply get this from the molar mass given on the periodic table. So next we see that moles CO2, that's going to cancel out like that. Okay, so we go through with our calculations. Numerator, get 132.03, and then 1 times 1 is just 1. So 132.03 grams of CO2. The next example, the third example, is going to be mass to liters. So we are given 7 grams of oxygen that react completely with an excess of NH3. So again, that just means that there's plenty of NH3 available to react in the reaction. And so we're trying to find how many liters of NO gas will be produced at STP. So now we're going to have to use a different conversion, which is that at STP, in 1 mole of substance, usually gases, there's going to be 22.4 liters. So just keep that in mind up here. So we're starting with our 7 grams of oxygen over 1. So like we used in the previous example, we're going to need to use the molar mass given from the periodic table as a conversion in order to get moles. So we're going to be starting with grams of oxygen, going to the moles of oxygen, because you need to go to the moles in order to be able to use these coefficients in their ratios up here. So moles of oxygen, and since we're trying to find NO gas, we're going to be going to moles of NO, and then because more specifically you're going to want the liters, so we're going to go from moles to the liters of NO, and that's where we want to be. Okay, so we're starting with the 7 grams of oxygen, and you know that in 1 mole of oxygen there's going to be 32.00 grams. 1 mole. So took our grams, got our moles, these units cancel out. Next, we're going to use our molar ratios from up here. So here we got the 5 moles of oxygen, and since we want NO, we got 4 moles over here. And then we want liters ultimately. So we come over here, we already have moles NO, and that's going to go on the bottom over here. So 1 mole of NO, you're going to have 22.4 liters. And this is all depending on the fact that it's at STP, which is standard temperature and pressure. So we're going to go through. We got our moles of oxygen cancel out, moles of NO, moles of NO, and we're going to be left with our liters of NO, which is what we want. So we're going to do these calculations here. We're going to end up with a 3.92 liters of NO. So the next topic we're going to be covering is limiting reactants. So by definition, a limiting reactant is any reactant that is used up first in a chemical reaction. It determines the amount of product that can be formed in the reaction. So when you're going to want to use these like procedures or techniques for your calculations is usually you'll be given 2 quantities of reactants, and then you must determine like which the limiting reactant is and like how much product can be produced. In the first example, we will have 25 grams here we go, of C3H8 that combine with 100 grams of the oxygen. And so we're trying to determine how many moles of water can be produced. So given our equation down here, when you're doing the limiting reactant problems, what you're first going to want to do is pick one of, or this is what I do, I pick one of the products that you're going to want. And so in this equation, we're looking for the water. So you're going to have to go through and do the same calculations that we're doing, the same stoichiometry, to determine, and you're going to have to do these for each of the different amounts of reactants, to determine which amount of reactant will determine, or which amount of reactant will produce the least amount of whatever particular product you're looking for, so in this case water. So we're going to start with the C3H8. So we're given the 25 grams of it. That's over 1. So same as before, we're going to be multiplying by the molar mass. So in 1 mole of C3H8, we're going to have 44.11 grams of it. So that gets rid of the grams here because we don't really want those overall. Then we're going to go back to our equation. So we have the 1 and we have 4 over here. So 1 mole C3H8 and 4 moles of water. Okay, so we're going to have two significant figures that we want. So you get like 2.267. So with significant figures, you're going to end up with like 2.3 moles of water. So we're done with that for the first reactant that we're given a quantity for. Next we're going to go on to the second, which is the oxygen. So same thing as above, we're given 100 grams of oxygen over 1. You end up with 2.5 moles of water. So once you've determined how many moles can be produced from each quantity of reactant, you have to go through and compare what's produced. Okay, so now that you've found the actual moles of water that can be produced from each of the amounts of reactant, you're going to look down, if you can see down at the bottom there, and you're going to compare the amount of moles. So for the C3H8, you were only able to produce 2.3 moles of water. And then for the amount of oxygen listed up above, you can only produce 2.5 moles. So obviously 2.3 is less than 2.5. So you can now deem the C3H8 as the limiting reactant. So now that you know it's the limiting reactant, you know that that's going to determine the actual amount of water that can be made. So the answer to the problem, which was the moles water that can be produced, is going to be 2.3. So just again to reiterate, the limiting reactant is going to be what is going to determine the final amount of whatever product you're looking for. And so because the C3H8 was able to produce less moles than the oxygen from the quantities that were listed in the problem, it's the limiting reactant, and therefore the answer is going to be the 2.3 moles. For this example, we're going to use the same type of calculations. It's just going to be slightly more difficult. So we'll start with the BaNO3. Take it twice. So we've got, and so in this one we're given volumes and then also the molarities of the solutions. So we're going to need to go from volume to moles, and then we're going to go to moles BaCO3 because that's what we're looking for, and then from there we can go to mass. So we've got our 20.0 milliliters of BaNO3 taken twice. And you know that molarity is simply moles per liter. So we can use that as a conversion. But first we're going to need to go from milliliters to liters. So we've got 1,000 milliliters in 1 liter. So next we're going to take our thing over here, and we've got in 1 liter, according to our example here, we've got 0.1 moles of BaNO3 too. Okay, so then we're going to take our ratio from the coefficients. We've got 1 mole BaNO3 2, and that goes to 1 mole of BaCO3. Okay, so we're running out of room here. And same as before when we talked about stoichiometry, we're going to go to our molar mass. So in 1 mole of BaCO3, we're going to be able to cancel out the units that you don't want. So here we've got milliliters, milliliters, liters, liters, moles BaNO3, moles BaNO3. Then we got 1 mole BaCO3, moles BaCO3, and we're going to end with the grams of BaCO3. So you go through and do all that on your calculator, and you're going to end with 0.394 grams of BaCO3. So I just, for time's sake, went ahead and wrote out all the calculations needed to determine how many grams of the Na2CO3 could be formed, or not Na2CO3, of the BaCO3 from the given amount of Na2CO3. And I did not realize this when I was writing the problem, but actually it's, as it turns out, they will, from both the quantities of reactants listed, the same amount of product will be able to be made. So I'll just go through and explain this again. So here we've got our given, and this is just a simple volume conversion. This is what we get from the molarity given. So you've got your moles over the liter. And then here we've got our mole ratio. And this is going to be from balanced equation. Next, this is just a simple molar mass from periodic table. And then you end up here. And so as you can see, we've got 0.394 up here and then 0.394. And so in this case, there is no limiting reactant, seeing as equal amounts of product or of reactant are combined in like the stoichiometric ratio. But say that one of them had been lower than the other, then the reactant that produced the smaller amount of BaCO3 would end up being the limiting reactant. And that's how many grams of BaCO3. The next thing I'm going to be talking about is the percent yield. And so percent yield is the ratio of the actual yield to the theoretical yield. For a chemical reaction expressed as a percentage, a measure of the efficiency of a reaction. As stated in the definition, the percent yield is the ratio of the actual yield to the theoretical yield. So for those of you who don't know, here's a refresher. Actual yield is obtained from like experimentation. So these are real life values that you get in the lab, or in the problem it'll say experimentally determined, yada yada yada. And then theoretical yield is what you get, it's obtained through calculations. So this is like if everything goes correctly according to my stoichiometric calculations, like no error at all, this is the value that you should get. So it's going to be the actual yield, so that's what you get in your experiment, so real life, versus in a perfect world you would get this example we're going to do with percent yield is just going to be a simple finding the percent yield. So first I like to go through and find the givens. So we have 20 grams of hydrogen reacting completely with an excess of N2, so that just means plenty of N2 that you need. So this is going to be the limiting reactant, that 10 moles of NH3 form. So in order to determine the percent yield, we're going to need, back to that little ratio, the actual yield over theoretical. So we have our actual yield from up here, which is going to be our 20 grams of hydrogen, or no, which is going to be our 10 moles of NH3. So ignore that. So this is going to be 10 moles NH3. So in order to determine the percent yield, what we don't have is our theoretical. So in order to determine the theoretical, we got to look at what the student is using in their experiment. So we have our 20 grams of hydrogen. Oh, first we're going to need our equation. So we have hydrogen plus N2 is going to yield NH3. So in here we're going to need a 3, which is going to give us 6, and then we put in our 2 over here. So we have 2 moles N2, 2 moles N2, 6 hydrogens, 6 hydrogens. Okay, so we're starting with our, and this is just from our givens, we've got our 20 grams of H2, and that's just, here I'll move this up, and that's just over 1. So back to our stoichiometric calculations, we've got 2.02 grams H2 in 1 mole, and then we come up here, we got 3 and then 2, so 3 moles H2, 2 moles NH3, and so yeah, we're trying to get moles of NH3, so we stop there, and when we calculate this out, we end up with 6.6 moles of NH3. So, in this particular case, somehow the student actually managed to produce more moles of NH3 than theoretical. I mean, which I guess could happen. You don't know what's going on in the lab. So going back to what we got up here, actual over theoretical. So in the student in the lab found there to be 10 moles of NH3, and according to calculations, we found there to be 6.6, I'll move this up, 6.6 moles of NH3. So usually the number on top is going to be slightly smaller because usually in some reactions or due to faulty technique in the lab, you're going to find that you're going to actually produce less than what you would in an ideal lab situation. So you're going to divide those, so 10 divided by 6.6. You're going to get 1.51, and so in order to turn that into a percent, multiply it by 100, and you're going to get your 151% yield. So in this particular case, the student did a very good job and was overly efficient. So for the final example, we're going to be showing how to determine the actual yield from the percent yield. And because we have the percent yield, we can go ahead and calculate the theoretical yield because we won't actually be doing any lab calculations right now. We're just going to be looking at the reaction and the ratios to determine theoretically what mass of water will be produced. And then from there, we will be able to multiply it by the percent yield, which was determined by the student, in order to find out what the actual yield will be. So, starting off here, move it up like that. So we're going to do some stoichiometry. We have our 25.0 grams of CH4 over 1. So just like all the previous examples, we're then going to multiply that by the ratio of its molar mass to 1 mole. So on top we're going to have 1 mole of CH4, and we know that that's molar mass is 16.05 grams. So from there we're getting rid of the grams and going straight into the moles. So then now we can take a molar ratio from up here. So we have the 1 gram of the CH4, and it's going, since we're looking for water, we have the 2 over here. So we have 1 mole CH4 to 2 moles of water. And again, we're just getting this straight from the balanced chemical equation. And from there, since we're looking for the mass, we know in 1 mole of water, there are 18.02 grams. So from here, we do our calculation, find, using correct significant figures, that there will be 56.1 grams of water produced. And so again, this is going to be our theoretical yield. Because we didn't go into the lab and get this from actually carrying out the reaction. We just did it here on the paper, so it's our theoretical. So from here, now that we have our theoretical yield, we can take the number we got, the 56.1 grams, which is our theoretical, and multiply it by the percent yield, which is our 0.782. And again, the percent yield is just showing the efficiency of the reaction. So by multiplying the theoretical by the percent yield, we can get our actual. Which in this case is going to be 43.9 grams. And so this all makes, as far as the theoretical multiplying by percent yield to yield, like giving the actual yield, this all comes from the percent yield equaling the actual yield over theoretical yield. So if you just rearrange that, coming down here, say multiply both sides by theoretical, you get the same thing as above. You get actual yield equals theoretical yield times percent yield, which is what you have up here.